Okay, we're starting the Zoom transmission right now. And in a few more seconds, I'm going to present Prosum. I have to mute my, yeah. And we'll start soon. My cats have a party here. Okay, good morning all. Today is a very special day. We have an excellent presenter, and his name is Prasan Bhattacharya. He is a professor of groundwater chemistry and coordinator of the KTH International Groundwater Arsenic Research Group at the Department of Sustainable Development, Environmental Science and Engineering at KTH Royal Institute of Technology, Stockholm, Sweden. He researches drinking water, contaminant from groundwater sources in different parts of the world, and is especially focused on geogenic contaminants such as arsenic and fluoride. He collaborates with several universities and research organizations across the world. He's currently leading a project on enhancing private sector capacity for scaling up access to safe drinking water, policy, system strengthening, and sustainable service delivery in collaboration with UNICEF Bangladesh. So, Prasan, you can start.
Thank you very much for inviting me on in this lecture series on IGCP 707 project on the different geogenic contaminants in the Altiplano Puna region. So, and where arsenic is one of the important contaminant what we have been working. So over the past more than 15 years almost, we have been working in Latin America, mostly Argentina and then Bolivia, and where we have extensively worked on the occurrences of arsenic, mechanisms of mobilization, and also mitigation to some extent. So the topic on which I'm going to talk today is on arsenic in global groundwaters, impacts and risk mitigation. And this is actually summarizes all the experiences we have had so far since we have started working. So who we are? So we, KTH Royal Institute of Technology, has acted as a hub of knowledge for international cooperation in water quality. So we have been performing for the past more than 30 years almost. We initiated a number of studies on research on groundwater quality. And even from international perspective, we play a key role in pursuing high quality research on water resources, both in terms of water quantity, quality, and also other water ratios of management specifically. And since 1970s, we have been actively involved in different parts of the world on groundwater resources, especially India, Bangladesh to start with, and then moving on to Argentina and Bolivia, as I mentioned, where we look into fluoride contamination, arsenic contamination, salinity, and also radiogenic contaminants to some extent. And then groundwater contamination related to geothermal energy sources. Ayaz is here. So we have been discussing about different lithium contamination linked with geothermal waters. And also in all these cases, what our focus has been basically to understand the hydrogeological processes in the aquifers leading to the mobility of contaminants and eventually developing mitigation strategy. So what has happened over the time that my interest has grossly shifted to a major extent after we have done this basic hydrogeological understanding. We're now focusing mostly on mitigation strategies. So before we get into the business or start talking about arsenic, we need to really get what is the global freshwater demand. So that's how we can really enhance or scale up our understandings, and which especially, and this understanding is needed to cover the emerging and growing need for drinking water supply, agricultural water, and where the global food demand is increasing and it's estimated to be increased by about 70%. And there is already a forecast of 9.3 billion people by the year 2050. So this really makes a huge amount of pressure on the groundwater scientists to really understand the water systems and to ensure global freshwater supply in the coming decades. And within this framework of sustainable development goals, it is also very important. So it's not only a challenge, it's a primary responsibility of we water scientists to really provide this or at least work out the safe drinking water sources. And this essentially needs a cross-border research, a global knowledge supply chain, which is absolutely necessary to cater all these challenges. So water is obviously at the core of sustainable development. So it's, as I mentioned, it needs for both for the domestic drinking purposes, agricultural industry, and energy production is uses, and also and all these uses are generally interlinked and often competitive. And in all cases, there is also ample scope of they generate tremendous volumes of wastewater that may cause pollution in different domains, be it in the agricultural field or be it in the groundwater. I mean, when you talk about geothermal energy production, and it's also a central issue in climate change perspective, like linking the climate systems to the environmental as well as different socioeconomic systems, where we need to address the water scarcity on one side, and on the other side, we also need to cater the risk of flooding in others. In any cases, whenever you have this excess or paucity of water in the region, or so we need to think about how best we can really cater our use our knowledge to devise essentially or move towards sustainable use of the groundwater resources. And the 2030 agenda has rightfully dedicated a goal, SDG 6, which encapsulates ensures availability and sustainable management of water and also sanitation for all. Just to give you a broad framework, I mean, this is not a very new diagram, so it's everyone knows about this diagram, but see how water is linked. SDG has 17 goals with 169 targets and 230 indicators for progress. And this has been resolved of what to be accomplished within a span of 15 years. And especially when we talk about clean water and sanitation, needs significant impetus to work in a very integrated manner together with other cross sections. So water is flowing across all these SDG boxes. So how do you really find the right track so that we can achieve sustainable use of water resources? So now if you focus more on the ensuring availability and sustainable management for all, it definitely, as I mentioned, and that's one of the major reasons why we are trying to discuss these things over the long distance through these different webinars, and how to really exchange our knowledge. So we have a broader sense. In this case, we have drinking water services, wastewater and different sources of wastewater, and water quality in the and cooperation and participation. So these three red blocks are most vital to achieve the sustainable development goals what concerns the safe drinking water for all. So when we talk about implementation for drinking water safety, now I'm putting just arsenic mitigation as a case example. We need four basic building blocks. First is the technology, and then we have to need capacity building, and then data science, data monitoring and accountability framework. We need to have open access, and importantly, we also need partnerships. So if we to look into the technology, what technology we have, we need to have smart monitoring techniques so that we talk about the data which comes out right from the groundwater in real time perspective. so that one can make better decision-making tools. And once you have the contaminants, we need to have and we need to apply locally adaptable technologies, and which are very critical if you want to achieve the sustainable development goals, especially. And of course, who is going to use this technology? So we need capacity building, and that also needs significant amount of information flow. It also needs investments to support the use, adaptation, and transfer of different technologies, and most importantly, public awareness. So we need to really make people aware so that capacity building is a real term. It's linked with public awareness and the dissemination of best practices. So here, I will just go back to the slide. International Water Association has a number of specialist groups, like for example, our specialist group on metals and related substances in drinking water is one of the most important specialist group, which is actually looking into the diverse suite of drinking water contaminants and how do we manage the groundwater sources. And this also walks around with partnerships, so that IWA or International Society of Groundwater for Sustainable Development. So we have different partnerships, and together with that, we also need to have several other existing alliances and to build upon them, to strengthen them for revitalizing different partnerships for sustainable development. So that's in a very nutshell what we talk about in terms of sustainable development perspective and water resources. Now, if you look into arsenic, especially, arsenic is actually listed as one of the priority drinking water contaminant in the SDG 6.1. So both arsenic as well as fluoride. So here I'm going to focus more on arsenic in this talk. So it's a metalloid, and of course it is one of the well-known carcinogenic element, and it comes in a very silent manner. It doesn't, you cannot feel it, but you feel the impact of this contaminant or as a toxic element in human systems, when it gets accumulated in different bioaccumulates in different food producers and all. Overall, it ranks 20th in abundance. So here is a picture of the native arsenic, which is in the. So looking into the arsenic in general, the environmental geochemical um, characteristics. So we have the two predominant inorganic species, arsenic 5 and arsenic 3, which are most prominently occurring in the geogenic environments, and where we have the pentavalent form is mostly occurring in the oxidizing conditions under neutral to alkaline pH, and the degree of protonation varies with the pH. And also under reducing conditions, this arsenic mostly occurs as trivalent arsenic. So these are the two most important. If you see this Bohrbank's diagram, so we have this. So what we have, this box shows the most groundwater occur in a mixed form where we have both arsenic 5 as well as arsenic 3. However, we see that arsenic 3 is more mobile because they are not sequestered on any or in the aquifer matrices. So that's how we have, whenever we see the mobility of arsenic, it's predominantly in the trivalent form. Like in Bangladesh, we have almost 96 to 98% arsenic 3 in water. As soon as they go over to arsenic 5, so they are mostly sequestered onto the oxide surfaces. So that's the basic the environmental geochemical characteristics. So if we look into the global occurrences of arsenic, we see that water resources, both surface and groundwater, are significantly affected. It can be the natural geogenic occurrences, as well as we can also see a diverse suite of activity, anthropogenic activities, and predominantly mining activities, which bring out tremendous volumes of arsenic or amount of arsenic to the environmental compartments, and thereby contaminating risks both soils, groundwater, surface water, depending on the situation. So if you look into this is a map which was first produced by Joshin Bunshu long time back in 2007-8. So we had a very selective number of points where we have seen some of the points, Brazil. Now there have been several new additions, Colombia, and also a number of other countries globally, which have shown high levels of arsenic in groundwater resources. And one thing which is really very common, which you see all along the western belt of the Americas, you see the highest of the occurrences of arsenic along. And on the other side, if you look into the Himalayan alpine chain, so we have a concentration of arsenic throughout this Himalayan out. So this is fundamentally controlled through the tectonics, which play a significant role in the distribution of arsenic in the global arena. So what we really see, and this one of the publications which we had in recently in Science of the Total Environment that discusses more about this these occurrences. And if you look into this, and what are the aquifer environments which govern, and these are actually classified into three broad groups: strongly reducing aquifers that we see in the deltaic plains, for example. We have several examples of reducing aquifers in Bangladesh, India, and also in Vietnam and Cambodia. In those regions, we have high flow, and then we also have reducing aquifers right in the Brazilian east coast region, and then we have arsenic linked with high alkaline and high pH groundwaters in the oxidizing aquifers as envisaged in the area around the Chacopampian plains in Argentina. And partly we also see such high arsenic groundwaters in some parts of Bolivia. And and then there is another category where arsenic is more linked with mining regions, where we have high band the aquifers which contain the mineralized in the mineralized belt, where we have arsenic together with arsenopyrite and other sulfides in general. So overall, if we see the population at this now, these numbers are reasonably old, but still it gives a indication that the impacts of high arsenic groundwater is essentially reflected through the population density, which is dependent on the groundwater resources. But this is just to understand the magnitude of arsenic, because even for if we talk about the Sweden for it specifically, in Sweden, in the private water wells, we have nearly 200,000 population in Sweden are at the risk of consumption of high arsenic in the private wells. However, these private wells are mostly located in the summer houses or things like in Umeå, for example, in close to Stockholm, we have very high concentration of arsenic, up to 70 micrograms per liter, as compared to the drinking water guideline of 10 micrograms. So if we go beyond to the India-Bangladesh field, so Bangladesh and West Bengal are one of the most important global arsenic hotspots. And the discoveries of arsenic have been discovered. They have been discovered since 87 in West Bengal and as early as 1993. So it's about more than 3 decades and 4 decades. This arsenic has been present in groundwater sources within the Holocene sedimentary aquifers. And in Bangladesh specifically, if we look into the thing, more than 25% on the shallow wells. Shallow wells means wells within maybe 100 meters or even shallower, have more than 50 microgram per liter arsenic. And then the overall risk, considering that these shallow tube wells are still in operation, we find that about 70 million. So now these numbers have decreased considerably over the past years, but still we don't have these numbers in a very consolidated manner, because we have new implementations which provide adequate safety. So these are coming up with the regions in Bangladesh, for example. This is the overall distribution of arsenic, but the probability of arsenic with high arsenic, for example, here you see the green areas with up to 10 micrograms per liter, and then we have 10 to 50 micrograms per liter. That is below the Bangladesh drinking water guidelines. So we have two type of green shades which represent the arsenic concentrations below the Bangladesh drinking water standard and the WHO guidelines. And the remaining parts, what we see here, the yellow and the orange and the red ones, these are extremely high concentration if you consider the drinking water guideline, the WHO guideline. So that's a very strategic question. What should be the safe drinking water guideline for Bangladesh? Because that's again a function of how fast or how the mitigation implementation processes are ongoing. So I'll be going into this in more detail. But now, if you look from the bank, we were talking about the Delta region. But if you look into the towards the west, we find that the entire Indo-Gangetic plain, for example, here has been washed through the sediment which comes from the Himalayas. And then there are two trajectories, one going towards Pakistan, where we have also have high arsenic in the region towards the west. And then in farther to the west, if you see Iran and other areas. All the areas have recorded have high arsenic groundwaters in this region. So all these light shade these areas are all the sediments, mostly Holocene sediments, which have high incidences of arsenic in groundwater sources. And this is the trajectory of discoveries of arsenic in India and Bangladesh in the area. What we see, the 1976, the first arsenic occurrence was discovered in Chandigarh region of in Western India, and then West Bengal 1983, Bangladesh 1993, 5, and then in 2001 it was in Nepal in the Himalaya, and then 2002, and then in 2002, 3, 4, we had number of occurrences both even in Assam region, which have. But in some of the areas, what we find, for example, in Assam, we find both arsenic and fluoride. That they are joint present together in the matrices. So that's really intriguing and also very interesting to see how do we see the coexisting contaminants in groundwater systems. And similarly, we also have had arsenic and fluoride contamination in Pakistan region, for example, in Lahore, in the area in the. So we have this sort of soup, and then we also have high arsenic and fluoride groundwaters in several other parts of the world, like in Argentina, and partly we have also discussed even in Bolivia, for example, in Santa Cruz region, in the plain lands of Bolivia, where we have this fluoride occurrences as well. So mostly what you see here, we see that arsenic is mobilized in reducing conditions in mostly along the river plains. And one of the important factors which governs the mobility of arsenic is the organic matter-rich sediments, which act as a redox driver for the mobilization of arsenic. So global scenario, I mean, this is we have already discussed here. So I just want to talk about the estimates of population. If we talk about Latin America now, so we shift our attention in the Latin American region. We have seen Argentina about our recent publication, which was given critical reviews of environmental science and technology recently. So that's got published, I think, last month, finally. So that's where we have summarized the latest state of the art of arsenic in the 20 Latin American countries, and the research which has been carried out over the last 20 years of work which has been prompted, because the research which started in the India Bangladesh region, so these studies have just laterally translated in Latin America, which gives more understanding of the gross behavior of arsenic in different water environments, and as an on we are enhancing our knowledge about the comprehensive drinking water safety. We are trying to identifying, or we are actually understanding more about the occurrence of arsenic. For example, this is a diagram which was first we talked about in 2010 or so. But there were several unknowns in several countries: Ecuador, Colombia, Nicaragua, Costa Rica, El Salvador, Guatemala. So now we have different groundwater sources which have high concentration of arsenic, depending, but the concentrations definitely are over the WHO drinking water guideline, but not as high as what we see in Bangladesh in the deltaic aquifers there. And if you see the population risks, we see in terms of national population in Argentina, it's quite up to 5.5, more than 5% population. Chile about 3.1, Mexico 0.4, like Peru 0.9. And in many cases, with time, what we are now trying to see that even not only drinking water, even in Peru, for example, recent publications by in the region by one of our colleagues, Deo Priamondol, she has been working on the Peruvian rices, which have high concentration of arsenic in the in due to the irrigation with high arsenic groundwaters in the region. But still, there are several unknowns which needs to be studied more in detail what to do. And this is some of our own field photographs from Argentina. This is from 2004. And this is a picture from Maria Elena region in Argentina, Santiago del Estero, where we have been working on people showing the physical manifestation of keratosis in the hand. These are the this is typically a field photograph of measuring the groundwater chemistry in the region. So that's how it's seen in this Argentina. So overall, if we try to summarize now the Latin American scenario, is being currently explored, and several studies have been undertaken, and several more are in progress. And different geological and hydrogeological conditions are still under investigations, and we're getting more and more data. So and this offers opportunities as well as challenges for future research on all major fields of environmental arsenic, for not only for designing effective safe drinking water options or treatment, or searching for alternate drinking water sources. Now, I want to make a flag an important point here. When we talk about water treatment, we should definitely focus first on low concentration sources, so that we do not on the other at the end, what we find, we should reduce the arsenic bearing sludge. So if you have sources which are low arsenic sources, that has to be treated. I mean, that has to be opted in the first instance to understand the especially the spatial variability of the contaminant in groundwater, so that you choose or select areas which are have genetically low concentration of the arsenic in. So if you look now, one of the important areas in Argentina, for example, in Chaco and Pampean regions, where you have Santiago del Estero has high concentration pockets in the region, and then we have Chaco and Pampas, and then Copahue, and then San Antonio de los Cobres, and that's in the Andean ranges. So these are the areas which have generically high concentration of arsenic linked with mineralized mineralized. Uh, these are mineralized regions in the Alps, in the Andes regions. So what we find, and then if you look in analogy with the Bangladesh scenario, this is just 90 degrees apart, so that you see that all the plain areas which are in front of this Andes mountain, they have this probability of high arsenic increases. With that, even arsenic is reported in the Resistencia region, in close to in Paraguay. So here, the rice cultivation and resistance. So there has been a number of publications, I think, by the Argentine Nuclear Research Authorities. They have been working here. They have high concentration of arsenic, and not only in groundwater, but even the rice produced in this region have high concentration of arsenic in the rice. So in the sources of arsenic, again, we talk about the predominant dissolution and leaching of arsenic from different volcanic rocks and also volcanic ash. And these are mostly of Andean origin. And then the second what I already told right now was about the mineralization and mining activities in the Andes region. And importantly, I would also like to mention about the Chile, the Antofagasta region, which is one of the regions which is well known for high concentration of arsenic over centuries. So there we have concentration ranges 100 to 10,000 micrograms per liter. So they're extremely high concentration of arsenic in this specific pocket which we look. So in more in detail, if we look into the Chacobampian plain, we have quite extensive areas with high arsenic concentration up to 100 to 200 milligram per liter. In the Buenos Aires region, we have Cordoba, La Pampa, and in the Chaco Plains and the Santa Fe province, some in the Salta province. So we have high concentrations arsenic extending over several south. So overall, if we look into the aerial extent, we have more than 100,000 square kilometer area, which has a potentially risk of high arsenic in groundwater resources there. So now slightly about the different the occurrences and the spatial variability trends. These are not per se what we are talking about geospatial technology, what we have started working while we are working now in Africa. We need to have this data and then try to reinterpret all these data in terms of spatial variability patterns so that you have this. For example, these are high regions, for example, high concentration of arsenic, high. But even in high concentration of arsenic, we see green regions. So what are the probabilities of getting low arsenic waters within this broad gross high arsenic domain? So these are the things which needs to be undertaken now. And partly I know that Israel Kino, he was during his PhD, he was looking at the spatial variability analysis in Rio Catari Basin in Bolivia. So we need to expand those line of work to understand the details behavior of arsenic in different groundwater. Now, if we look into the spatial variability of arsenic, we also need to understand what are the hydrogeochemical conditions which really facilitated this, makes these mobile. So we need to understand what are the combination of effects of different groundwater solutes in the distribution of arsenic. So that's the important aspect of arsenic, which when the distribution in groundwater we need to understand more. And these are again some of our old understanding. This was from one of my oldest publication. I think this was from 2006. We tried to see that these are again the impact of pH and high arsenic domains and how they're all linked to each other. So this was a general understanding of bicarbonate links with the total arsenic with bicarbonate, with links with pH, and competing solutes like phosphate in the oxidizing aquifers in general in the region. So Argentina, if you look into, this is 1.5 to 2 million population at risk. So again, this is again coming back now. So if we look into the arsenic remediation in water, we have a broad spectrum. This is again from our paper, which was published in the best practice guide on arsenic removal and remediation for drinking water supplies. So we have 6 broader categories of interventions. We have precipitation, these are treatment options, adsorption, membrane filtration, bioremediation, oxidations, and source substitution. So what is important from low income perspective in the regions where we have low income areas, so we need to search for a source substitution variety, which means that we have to search for low arsenic groundwater sources. Then again, we have options for treating surface water and then rainwater. So among these two, for example, come on increasing burden on the groundwater, in surface water contamination, we are mostly, and people's perception about safe water is always the groundwater is the preferred option. So we need to go ahead with source substitution. And within that framework, that's how we started off the well-known project, Sustainable Arsenic Mitigation, that CEDA project in Susmit. So where this is essentially, we are talking, we go get back to the same diagram. We are working in an area in Matlab, which is located in a high arsenic domain. And we see that drinking water supply mostly 90% depends on groundwater, a very limited focus on surface water sources or other sources. And most accepted option is hand tube wells, and that you see also in Argentina, also in the rural clusters, we have hard arsenic tube wells as one of the main important source of groundwater and drinking water. And then about more than 90% of the tube wells are privately owned and installed by the private tube well drillers. So that was the main rationale for this project, which was implemented as a community-based and cost-efficient strategy for targeting safe groundwater. For and then it was also optimized on the basis of local knowledge, means the local knowledge of the tube well drillers and the technique. So if you look into and now I'm just going through this, one of the worst affected areas in Matlab. And then there has been a number of previous studies with BRAC, ICDDRB, and funded through the CEDAS support. So if you look into different treatment options here, we see that a remarkable failure trend of all these treatment technologies which have been provided. So what we see that there were several number of different filters which were actually implemented. They were given to people, but none of them showed a impact in terms of regular use. For example, filter to remove bacteria, the arsenic removal, ARFs, arsenic removal filters, they were none of them were functional. So only the most important source which were actually provided and people were relying most was the arsenic safe tube well. Now this 10% drop, which is shown non-functionality, this was basically due to the hardware issues like the different so some non-functional tube well heads and so on. So these were some of the important aspects. So when we talk about the drillers approach, so what it comes from the it basically comes from the local drillers initiative. So what they had they had looked into the sands or the sources which have diagnostic colors. For example, when they have fine sand with red and yellow color, and was no apparent iron concentration, and they were branded as a good water. And so the implementation of safe wells were defined by the local drillers where they don't find any arsenic. Now we know that there is an inherent relation between iron and arsenic. So if you have no low iron concentration, we mean that it is not the redox limb interface is much higher than what. And so what we see here, we have low iron and also low arsenic. So there is the spin-off effects of the initial location. And then again we have see the 60 to 80 feet, which is roughly 20 to 40 meters. So there are low arsenic concentration in the regions in these areas. So here what we see here is a series of sand sort by the local drillers, and these are the hand percussion drilling. It's a manually operated some hand suction assembly done by the local drillers. So these are actually, this is a diamond shows that we have the, as and on the drilling process goes on, we have a number of sand which comes up and which goes from the black color sediments, which goes over transitions over red sand. So what we see in terms of arsenic concentration in groundwater, we have the black sediments, they have arsenic concentration up to say 300 up to 350 micrograms per liter, whereas in the off-white, say in the off-white and red color sediments, arsenic concentration reduces drastically, and it is definitely below 10 micrograms per liter in the red sand aquifers and also partly off-white and white sediments. So it's important, was what we really, was very important to foster this knowledge, which is currently implemented by these local drillers, and how do we really use their knowledge for arsenic mitigation purpose. So what we did actually for this practice was followed up with the local drillers, and it was systematically carried out with the collection of different sediments from at different levels up to a depth of 250 meters, and approximately 2,240 samples were collected during this project implementation. And what we find here is a series of different colors based on the Munsell soil color chart. Munsell colors were assigned, and then these were basically this was essentially done using the visual ocular investigations at that stage, and it was cross-verified by both by the field inspections as well as by us in the back after we have collected sediment. So we broadly classified these sediments into four distinct categories in terms of this is a typical Munsell color chart, and then we divided this into four quadrants. So what we really see that in each of these Munsell color charts, we have four quadrants, what is the lighter variety in this quadrant were all classified under the white categories. And then when we have more towards off-white and yellowish, so that's the hue increases. So we find the off-white and then black, darker hues with the black sediments. And then in the right, we have the red sediments. So these are the basic criteria for the sediment classification. And together with that, what we see here, what we found that there were overall, we had 60 shades, and each of the 60 shades were found. Finally, we assigned these four colors in these different shades. So what we see here now that we have, then we could identify what are the relative risks of high arsenic in groundwater. So in the black sediments, we generically had very high concentration of arsenic, but as and on we move from black sediments to white and off-white and red, the concentration of arsenic decreased significantly. And then redox status, of course, together with that, we had highly reduced in the black sediments, and then comparatively and less reduced or in the when we moved over from the black to the red sediments. So this was the publication which emerged out of this work, and this was the one of the first papers where we really translated this local drillers' knowledge into a resource and scientific validation of the sediment color, and that's the sediment color tool was proposed and implemented. So this is again the Munsell color shades and codes with different categories, and then and this the physical this color tool was used essentially to guide the future installation of tube wells. So then these colors, what you see here, they are the real colors when you drill the wells, and what sands which are recovered from different drill cuttings. So what we see here, so we have different color shades. So here what we see that each of this black color, we have three different subgroups, and this and then we have in all these categories, we find that the arsenic concentration are high in the red categories, and then the white, off white and red, we have low concentration of arsenic. If you look into the temporal variability, so because during the implementation we had a long-term monitoring of the groundwater wells, so we didn't see that there has been remarkable changes. So the overall variation in arsenic concentration remained to a major extent homogeneous, so that there was not much of variation. So one cannot really see that the concentration of arsenic is increasing drastically. So in the red sands, for example, 29 meters, 52 meters, so they were all high concentration of arsenic. But in the lower end, when we talk about the safe aquifers, when we identify those, in all those cases, we had arsenic concentration well within 10 microgram per liter, and then of course in a few cases in 95, but the when very top they went more than 10 micrograms, but again it was below 50 micrograms per liter in the region. So this is again, I mean, in order to come, how do we really communicate this research results? So then what we see that what we found in this region, that when you have low arsenic, we also looked into the distribution of manganese, because manganese is also a redox buffered element. So this is again what we see, that when arsenic is low, we find our iron is low, but some cases we have a high manganese. So this was again a important discussion which we took, that how do we really combat the issue of manganese, because if we are implementing wells through CEDA's intervention, so we need to ensure the comprehensive drinking water safety plan. So, so we need to move forward to understand the different sources. So one of the important sources, what we found there was the same intermediate tube wells, which I'm not touching upon that because that's, and in the intermediate deep tube wells, in those cases, we found about 90% of wells at intermediate depth were low arsenic. And this is one of the, this safe with this sediment color tool paper. It got the TUDAP Global Drinking Water Best Paper Award in 2019, and was Mohammed Hussain who was the first South author. So this was published. And then looking into the overall strategy, then how really we translated both, combined the technical aspects and social aspects. So we, based on identifying the different social, and this is again a new branch which is coming up now, social hydrogeology. So it's essentially understanding the user perspective, the groundwater users, who are the end users. So we have the technical aspects, understanding the groundwater, and here you see the intermediate deep tube wells, which have low, to a major extent, low arsenic concentration, low manganese options for the deeper wells. And, and so the integration, so seismic strategy brought in the combined effect of both technical and social aspects. So opportunities and strengths on a global scale, it essentially uses the local knowledge and technique. It's accepted and adapt and easily adaptable by the community, cost efficient, and the rural and it is can be used within the RWS, rural water supplies programs, or to private sector to scale up drinking water sales. And this is one thing which really brought us to the platform where we try to look into the enhancing of private sector capacity. So now when I was talking about the having and dealing with the sediment colors, so the manual or ocular investigation was slightly, it could be further improved by designing a digital technology. So that brings in this digital tool called ASMITAS, Arsenic Mitigation at Source. So this tool was initially installed to bring up these physically identifiable colors into a digital media. So what we essentially did was to importantly to get the informations which are collected from the field, right from the mapping to the sediment colors on a digitized platform. So which give much better option for data synthesis and data accumulation. So it's essentially getting the information right from the big files to a digital platform on the maps. So it's essentially enhances the transparent decision support and enhanced accountability, both in terms of transparent decision making and for site selection, as well as for the decision makers in the local scale, at the local, in the Bangladesh, for example, the Department of Public Health Engineering, how they can use these methods. So now before getting further, so what we really could understand, that we need to understand the overall approach, what should be for arsenic mitigation. So we have the system strengthening approach for the government and stakeholders. What are the policies and how do they look into the different private drillers and their perspectives and how they are covered in the systems approach, and which protocols are there, perimeter site selections. And then on the other hand, there are several thousands of local drillers. How do we really map these local drillers, but do a survey, interactive mapping of with them, and then monitoring and hydrogeological, and within these different the hydrogeological monitoring of the areas, and then capacity enhancement. So that's the thing. And then on the other hand, the UNICEF, they were also working on arsenic safe community and arsenic safe union projects and arsenic safe village concepts. So these were actually a mix, so that in the longer run, there was a good opportunity for us to combine the UNICEF arsenic safe community, arsenic safe union. So it is abbreviated ASU now. So this is meant to bring a harmonized approach for looking into it. So what we are doing now, so we have been doing the policy protocols reviews, and then strengthening capacity of these difficult critical mass of local drillers and master drillers. We have the integration of the seismic protocol into the DPH UNICEF arsenic safe village or union projects, and then in a further one step forward to support the government of Bangladesh to establish the registration and certification system for public as well as private drillers. So now this is the facsimile of the of a passbook, or it is a certification for the local drillers who will be working with the local for drillings. And then it also we also have envisaged that we'll enhance collaboration with the health department for arsenicosis patient management, like looking into the different stakeholders with when you are providing low arsenic water, how did the health status changes. The EPSC, it is essentially connotes enhancing private sector capacity. That's the current thing. So this is a information source of arsenic in groundwater based on the recent mix survey, not recent, 2 years back mix 2019 survey. And in this project, we focused on 3 areas. As in previously, as we mentioned, we worked only in Matlab Upazila. So now we wanted to implement this EPSA in 3 other upazilas which have a contrasting geological characteristics. One in the coastal areas in Asasuni, it's in Satkira district, where we have a predominantly challenge with high salinity groundwaters. And then we have in Daud Kande, which is more similar to what we have experienced in Matlab. It's more similar. And then in the north, we have Goan Ghat in Sylhet, that is very close to the border with Meghalaya in India. So in all these areas, what we see here in the Asasuni area is most remarkable, about 66% wells which have high arsenic concentration, more than 50 micrograms per liter. And then in most of this region, in Goan Ghat, for example, 33%. And in Daud Kandi, we had around 56% shallow wells with high arsenic concentration. So what was the approach? What we did, we do the situation analysis and essentially identifying the hotspot based on rapid testing of the wells. And then second step was the mapping of the local drillers and their capacities. What we can see that based on these are the GIS profile overlays of the drillers' knowledge based on interviews. So what they have actually provided us with their data based on their perception or their practice rather, how they have given the distribution. So distribution of different sediments here, and then the overall arsenic distribution in the different pockets of the intervention areas. And then what we look into the social aspects, and then primary investigation of piezometer installations for for the targeting safe aquifers in the region. And then in order to enhance the transparency and decision making through the digital platform Asmitas, how these different, while doing this, installing the piezometers, all the data were actually captured in the field directly. So now just more zooming into the different areas. So these are the drillers hub. And what are these hubs? They are actually the local hardware stores where you get. So each of these hubs have a set of local drillers who are affiliated to these hubs. And this is actually, you can compare this thing like universities, and all the professors are affiliated to universities. They're almost similar. All the local drillers are affiliated to these in the hubs, the local drillers hub. So they get, and in many, so if you locate yourself into this drillers hub, then you can get an overall picture of the entire intervention, how the local drillers are doing. So we had 29 of such hubs in Goan Ghat and 13 in Asasuni and 38 in Daud Kandi region. So this is one thing. And then subsurface geological investigation based on their practice and then these are again, these data comes from there, what they actually provide, what are the depths of different sands and colors and sand, silt, clay, and what. So these are done to this. And then when you talk about the transition to Asmitas and how do we do it? And in this case, we Asmitas field in application. So you feed in this information to the while you're drilling. So what you see, instead of a handwritten to the lithologs, what you see here, this is the digital PDF output based on the Asmitas data, what we have been feeding in to the Asmitas. So, and this is one of the resource which we use now for enhancing the digital water platform for the Aspetas for scaling up access to safe water. And here, what is important, what we do here is that we have the same set of samples, but what we use now, we use a NIC sensor. It's a sensor which actually is linked with Bluetooth connected to the app, Aspetas app, and that's what documents. And this actually circumvents the entire board log description, which needs to be done by hand. So you can have all the information located onto the app. So you have this idea over aquifer mapping in the region. So we have this different little logs which are coming up, and then on the basis of this data as a data capturing tool from the in the field, and from there you get into the interface where you have the opportunity to build up a big information network so that you can visualize these different drilling results. So again, when we talk about this, so this is again, we need what are the techniques which are actually used in the digital water platform. Is we use the big data in safe drinking water interventions is essentially to systematize, assess, and validate the water quality data and the sources and the acquisition of the new data. And then we can also do water quality modeling for both surface water and groundwater, depending on where you are, what depth and all. And then it also has an opportunity for co-creation with different local stakeholders like the DPHE, government stakeholders, or even the NGOs who comes in assistance during the interventions, and which are very of paramount importance for the integration of the local knowledge in the context. So what we really need is the interfaces we have the IoT devices in the next step. What has so you can have a real-time information flow from the wells to the decision makers through different the survey both by BI services and cognitive services, and in the and everything is managed through the application, the apps, and the cloud-based data management system. And so knowledge management system, which gives to data visualization. We have models, we have special maps, and then enabled through a GIS-based technology in general. So when we talk about the model from the visualizing the aquifer geometry, we need the borehole database and the hydrogeological data management using the GeoGIS is one example of which we are working together with Rambol at this point of time. So we have this data capturing through the Arsenic app, and this facilitates automatic generation of visualization of bore logs, interface with the geological and hydrogeological softwares. We can use the interface with Arsenic and different mobile apps, and this different apps can be again be interlinked depending on when there are thousands of apps which are currently in the market globally. So how do we can really make use of each other and try to focus to streamline the flow of data through the different apps in a more in a very reliable manner, so that we have the data security and safety, because water quality issues is of very important in terms of data security and water quality procedure, how it has to be designed and implementation for different data capturing processes. And of course, that the important thing what I'd like to mention here is the DPHE, for example, the Department of Public Health Engineering should have the ownership of the processes and also the servers and the programs which they will own, and that's what this do. So we have the data from the local drillers through the app, to the models, to the GeoGIS platform, and from there you see the lithologs, and then you make a bigger picture of the aquifer geometry and then this data can again be visualized and seen onto the app, and then finally the local drillers can also see this thing. So when they are actually implementing, the long-term goal is to see that when they're actually operating in the field, they can also have a prior information when they plot the data. And then the big data for groundwater management, the drinking water safety, DWS. So what we see, consolidation of data. So this again, this is a real-time application of through where we can find the different well informations on arsenic, and this is example of arsenic, but we can have it for the entire drinking water safety parameters. What we can really depict right on the on the applications. So this was about the broader perspective of drinking water safety planning and also implementation. Another aspect which we have also worked in the overall in the past is about the regulatory status. I mean, arsenic mitigation and arsenic removal technology. Then this work has been jointly done in collaboration with AWI Water Cycle Research Institute, and this was again a broader term precipitation, iron manganese removal, coagulation, filtration techniques. And then what we actually did, the advanced oxidation, coagulation, and filtration technology, AOCF technology for reduction of arsenic to less than 1 microgram per liter. So this is again a small slide which presented in the Mexican conference there. Essentially reducing arsenic to levels 1 microgram per liter, which has a huge promise in all developing countries, because essentially it is not a process per se, it is actually an add-on process to simple iron removal plants, which is in operation in many parts of the region. So we have three basic steps with U-oxidation, because as I mentioned, the predominant arsenic is in arsenic 3 forms, so pre-oxidation of arsenic 3 to 5, and then sorption of arsenic 5 on iron hydroxides, and then filtering of this iron hydroxide co-precipitates from the matrix. And then that's how we use different doses of oxidants. We can use KMNO4 as one of the oxidant. We have, and then we can also have a dosing of ferric chloride for enhancing the iron, for enhancing the arsenic sorption. And this is one of the publications which was done through Arslan's PhD thesis, which was dedicated on arsenic, removal of arsenic to low levels of arsenic. And then we also need to see the impacts of different different co-solutes in groundwater. What are their impact on the removal, and both calcium, phosphate, silicates, nitrates, etc. So this is important steps. And then this is again a process plant in Brabant water in Netherlands and Breda. So these are the typical cascades what we see in the groundwater, the aeration processes in the plant, what we see. And then, I mean, this is just to show some of the platforms for international cooperation. And I mentioned about the IWA specialist group, metals and related substances in drinking water. I will encourage you to join this specialist group if you have not done so. So we have about more than 900 to 1,000 participants, members in our specialist group. So we can have this sort of an enhanced local knowledge. And then I was talking about best practice guide on the control of arsenic in drinking water, which was done, this was in 2017. It was a long project, starting 2012 and ending in 2017. So 5 years program. And then this was again, this is a guide which was series produced by the IWS specialist group, and is a state-of-the-art compilation of a range of scientific, engineering, and regulatory and operational issues linked with the control of arsenic. And then, and then we have this International Congress on Arsenic in the Environment, which we had last month. And this is the 3 volumes, and this current Netherlands volume is in progress. This will be coming soon. So we are starting off with this one. And with that, I would like to welcome you all to the 9th International Congress in Bangladesh, where we'll be possibly looking into going closer to the local drillers and try to experience there. And by then they will be also be trained in using the Asmitas app to work on them. And then I would like to thank you all. First of all, my PTH and our financing partner, IWA, is the Team Sweden, as it's called now, the CEDAS. And then the UNICEF has been supporting, and together with all our partners, our digital partners, Excel Dots, DPHE, Government of Bangladesh, Rumble, University of Dhaka is one of the university knowledge partners. And of course, all the collaborators of the KTH Groundwater Arsenic Research Group, including you all who are here. So a big thank to all of you. Gracias por su atención. Thank you.
Thank you very much, Person. That was a great talk. We have a lot of questions in the chat, and some some other expressions. Nevels Niasi says, tremendous, excellent talk, Prosun. And Rafuya Sahu, great research work and excellent presentation. Congratulations to Professor Bhattacharya. You have truly shown the way how to the global research can solve local environment issues. And he has a small query. I need to know, can climate change play a role in arsenic, groundwater contamination? Is there any study reported from any part of the world? If yes, then how can we manage this?
That's a very good question, actually, Nabil. But actually, this is a one question which we are trying to look into. One of our students, Regina Arunda, she was actually very much involved in understanding this climate change issue and how, especially if we look into climate change, I mean, especially from African Tanzanian perspective. So how do we see I mean, the question is that how do you really envisage what can climate change do with arsenic? So what can do? We can have extreme drought, which means that there is a lack of water. When there is a lack of water, then there is no flow. So we have the aquifers will go dry. There will be no water. So you feed in more oxygen into the aquifer system, especially the shallow ones. So you invoke a question that you lead up in a situation where there's a water is a deficit item, and there's no, and we have oxidizing situation, and in such situation you have limited mobility of the contaminants in general if you want to sequestering effect. So that is one thing. Second thing is that when you have high extreme rainfall events, then it's a question that what sort of, then you enhance this, reverse the system, that you have this water logging question, then that can really induce certain reducing conditions. Now, if we see looking back into our time series monitoring of the seismic wells, for example, we have done a periodic monitoring over consequent dry, wet, dry, wet, dry, wet. So when we see the arsenic concentration levels, what we see there, it's not, I mean, apparently there is not much of change what we have seen so far. So, and that's really a question. I mean, to what micro level one can really go. I mean, I know there was a couple of studies from in EWAG few years back, probably, where they have been looking into the mobility of arsenic, which varies within diurnal changes in arsenic concentration at a micro scale. So that again, so in perspective, you see long-term effects of arsenic in terms of climate change, we may expect some sort of radical changes. But the question comes that how long the changed situations or conditions prevail. So if iron, for example, iron precipitates under the dry conditions. So if they continue for over now, I mean, you don't expect that high iron doesn't crystallize that rapidly. But you need to give that time, so that 2 years, 3 years perspective. So when you have high crystallization, so together with crystallization, you can expect that initially the arsenic which was absorbed onto the flocks or so they can get the arsenic can move out when they are crystallized. So that's one impact. And then, but still, I think we need to do much more studies, especially looking into the aquifers under extreme change climate. I mean, dry conditions or wet conditions, so that we see that we have one spell of rain now, for example, in the independent in India, when we have this monsoonal climate. So we need to do some more systematic measurements in real time basis, so that we can conclude to a major extent.
And another question is from Cecilia de Vergaso from Chile. Which is the concentration of arsenic in Northwest Provincia de Buenos Aires, San Antonio de Areco, and which is the source?
Well, in Buenos Aires, in the entire tract, there are three. I mean, one of the important sources are, of course, the when we talk about the sedimentary sources comes from the the Andean mountains. Number one. Number two, it's also the volcanic ashes. So now, if we see the long distance transport of the volcanic ashes, so that's an important source, and that is more widely spread out over the continent. So we see not in terms of, for example, in Santiago del Estero, we see volcanic ash beds. So we have those. We have seen volcanic ash beds in La Pampa region. We have seen in Santiago del Estero thick beds about 30 centimeter, which I have personally seen those. So that's one thing. So and there we have this which when the leaching from these volcanic ashes, so they bring out not only arsenic but also other co-contaminants like uranium, vanadium, and so these are some and fluoride, of course, which comes out. So we have a number of sources, but especially in the tract which is much more towards in the eastern part, close to the Uruguayan border. So, but there also we see the impact of these volcanic ashes significantly. Plus, also in the deltaic region where we have the culmination of the sedimentary processes, so that how the sediments are brought in there and how they're mobilized under different reducing conditions.
And we have a question from Kirk. Kirk asks, does DPHE have control of the program? And if so, are you comfortable they can do this successfully?
Well, that's a question, very good question from her. So that's actually, this is one thing which we are now working together with DPHE. And how, because DPHE is now having a huge project in hand right now, arsenic risk reduction project, ARRP in Bangladesh. It is about 450 million US dollars project, and that's now we are actually now writing a project for technical assistance through UNICEF to this arsenic risk reduction process. So I mean the timings are a bit offsets, but the question is in this project what they are actually doing. They are doing firstly the arsenic screening of the wells, and number one, and then from this screening, and then we are going to add on this is system strengthening approach towards the government. So this is again a slow pace, a special molding. We have through our EPSC project, we had a number of capacity building, some workshops, both with the local drillers and all of the local DPHE personnel, which again facilitated through the DPHE central headquarters. So it's not a one-step process; it's a repeated iterations. So we need to say that what are the good things about. So and these things need time, and that's what we even during the Arsenic Congress, we had one full session dedicated with the DPHE people during the Arsenic Congress where we discussed each of these fine-tuned this is. So you need to fine-tune each and every aspect to see to just to demonstrate the beauty and to what extent the government will be capacitized or government will be strengthened by implementing the the different methods. Like for example, in terms of when we talk about the digital water platform, so how best we this will really enhance the transparency of the operation, enhance the private sector capacity, because UNICEF also currently has a vision to enhance the private sector capacity, because part of the work DPHE is doing is also now has to be done through different NGOs, and how these NGOs together with the local drillers are integrated in one platform. So that's a important step, and this is currently in progress. So we need to, and each of these components which I have discussed now are going to be a part of the work which will be going on in the next 4 years phase.
Thank you, Prosun. And Cecilia de Melgaso again is asking, the database for the decision support system is only from Bangladesh?
Our database, actually, I was trying to develop it for Bolivia also. Now we have so much of SIDA interventions, so much of data has come up there. How do you really assemble this data? So big data assembly. So we have, and this is also an operation which is we are currently discussing how do we move forward with replicating. And then the important thing, the lessons which you're learning from Bangladesh, how this can be translated in a result in a South-South cooperation unilaterally, so that we have the Sweden from the north and then all the South countries, how we can really transfer our knowledge and work together on the in a South-South cooperation.
And Maria do Rosario Melo is regards from Portugal. How will high concentration of phosphate carbonate will interfere in the water treatment for arsenic?
Well, that's again a very good question, and it's a process technology. I wish I had Ashlan with me too. But actually, the thing is that when you have high calcium, there are some important aspects of the water chemistry. For example, if you have high calcium, and how it facilitates or inhibits the arsenic absorption capacity in the wells. Now, the question is, which water are we talking about? In Bangladesh, if you look into water which is high calcium bicarbonate concentration, the young waters, the shallow groundwaters, which is CA bicarbonate type waters. So in those cases, removal of arsenic will be definitely be a part of tricky. So we need to definitely that will have an impact on the removal capacity, number one. And then secondly, may also be impacted through the presence of high iron. For example, if you have high iron, if you are putting if you are putting an aeration, for example, you have iron hydroxide, and if your redox capacity doesn't go that high, your already water is reduced. So first thing is that you enhance the precipitation of iron hydroxide. So if you have iron, siderite is one of the solid phase which is controlling the dissolution of arsenic and iron, right? So if you have siderite, FeCO3 to CaCO3. So these are some of the important baseline evaluation needs to be carried out first to look into. And then of course, then we also have the high concentrated silica. Silica concentration in wells also vary between 16 to 18 to even up to 20, 25 milligram per liter silica in different groundwater sources. So these all have an overall impact.
Okay, person. I'm going to read two more questions.
Calcium arsenate.
Two more questions from the chat, and then Noemi will make questions from YouTube. And if we have time, I will finish the questions from the Zoom platform. Ayas from Chile is asking, thanks, Dr. Prosen. Your presentation is a roadmap for all the areas where the studies and remedial measures have a long way to go compared to Bangladesh and West Bengal, India. Thanks for motivating us again, as always. Brandon from Chile, thank you, Prosen. Excellent talk. Have two questions. Regarding the distinct sediment types that were studied based on color, can future wells be targeted at specific depths to minimize arsenic concentrations from extracted water, or is the stratigraphy too complex? Highly mixed sediments types and waters. And the second question, from your work in South America, have high arsenic concentrations been correlated to specific volcanic rocks, parentheses felsic? Those are two questions.
The first question was about the
sediments, the color of the sediments.
Yeah, actually, that is one thing which we are actually working right now. Because I was mentioning about EPSC project areas. We had 3 areas. One of the area was the coastal area, where we have they are actually the important issue here is a specific physiographic setting is important to understand. So we need to see and really evaluate, do a proper hydrogeologic evaluation when you talk in terms of in terms of the differences in these hydrogeologic settings. So like for example, in the northeast, for the Goan Ghat area, where we have high arsenic in a belt which is so-called in the region. So that is drastically different than what we see. And thereby we need to, and that's where the current our intervention is trying to understand what strategies, what is the underpinning mechanism of these so-called these safe zones, or what are these sands. So they vary considerably. So that's why this EPSC project gives us we had a very sound information or information about the areas where we have this red sand aquifers, both in India and also both in Bangladesh. Daudkandi is not a major problem. We see the oxidized aquifers very fine. We see in the Nadia district in West Bengal, so we can translate directly. But in areas where we have this, the sedimentological characteristics vary. So there we need to really distinguish the specificities of low arsenic concentration. So that's what we are now trying to, now in this phase we're trying to design the sediment color tool based on the local hydrogeologic settings. So that is important. So understanding the local hydrogeologic setting is the key to the. And secondly, the second question was about in Chile or in
South America.
in South America.
Yeah.
South America, of course, I've seen, for example, in Bolivia, we had this red sands and gray sands in the Altiplano region also. Because anyway, when we talk about the Vaishalian glaciation, deglaciation period, so we see in Bolivia, for example, we have this red sand. Mauricio knows about when we're driving through the red sand horizons on the surface. So we had everything got red colored. So those things, and then we see the gray colored sands. So and that's where we just tried to understand the differential behavior of arsenic in those aquifers and the types. So we see those difference. And then of course Israel Kino, he also looked at the sediment colors in the Rio Catari Basin also. So there is a significant impact of different sediments and the distribution of arsenic.
Okay, Noemi, can you go with the Zoom, the YouTube platform, the questions there?
Well,
28 questions.
First, I would like to acknowledge Prosum for the excellent presentation, and I will proceed with some comments or questions also. Blaine Kliskey says, thank you for the excellent presentation. Well, then we have two questions. One is from Osvaldo Ramos, and he's asking about which are the aspects that we have to take into account to investigate in arid zones as the Altiplano in Bolivia related to arsenic and the climate change.
Mauricio, your question is very tricky. So, I mean, it's really something which there is no ready answer directly, because what I can say that this will be quite speculative if I say so, but it depends on the type of specific setting, So we need essentially to understand the hydrogel groundwater flow patterns, how it is flowing. So if you have no rainfall, I mean, so-called hydrological drought situation, and maybe in extreme climate change situation. So if you see a hydrological drought, so then you are actually delimiting the groundwater flow significantly. So what that can actually result to? Yes, what you can that results in a very limited flow, so that you are solute, they get concentrated. So you are likely to enhance concentration of the groundwater solutes in specific domains where you have the groundwater basins. So these are called groundwater basins. Like even we have seen in Argentina, for example, some groundwater pockets where we have seen 3,000 microgram per liter in an area, which are definitely in significant pockets of high concentration arsenic. Like in the diagram which was showing that red areas in Santiago del Estero province. So these are the results of some essentially very dry spells. So you have the high evapotranspiration, potential PET is quite high. So you have, and then secondly, it also may result in developing this carbonate concretions, ferricrete, silcrete, depending on the water chemistry. So that those things are quite significant. And then, of course, how deep is the groundwater how deep is the aquifer, because that is again going to control the distribution. Like and this is again the interesting point in Africa, for example, when you talk about the aquifers which have very old water, for example, what happens? So you have this enhanced, increased concentration of different solutes in those waters.
Okay.
Did I answer your question?
Oh yeah. Well, I think so because Osvaldo is in YouTube. Well, thank you, Prosum. And then we have a comment by Jessica Murray that she says, "Hello, sorry that I can't be in Zoom. Thanks a lot for your presentation, Prosum." And she has a question. Do you think that asmitas can be applied in the Altiplano Puna or the Chaco-Pampian Plain?
I would say yes. Yes, but that's definitely we can apply it. Because whenever we have, I mean, this is again, this is asked as a tool for data capture. So whenever you have a installation of tube well number one, so you can get the thing, and then you can also do to actually add on retroactive data onto the platform. So that's again possible. So it's essentially it's a data. The field-based application is the first step what we are trying to work out now, so that it becomes a ready to handy tool for the digital data acquisition system. And then from the historical data we can use so that we can import the data which is from the big database you generate, and from there you can do import this results what I've shown in the what I have shown here in the past.
Okay.
So for this some situation, what you see, you have this data from the ground, so you can build up retroactively the groundwater scenario. Yes. So and that's an interesting project which is proposal which is ongoing right now. So we need to move on the digitalization of groundwater resources.
Okay. Thank you, Prosum. Osvaldo answers thank you or the answer.
Okay.
Thank you, President. Well, we don't want to take a lot of more of your time. I'm going to read one more question and all the congratulations that we have received in the chat, and the questions that remain left. I'm going to send you by email, and I see if I can send it back to this group of attendees. And Cecilia Mergazo he said that they are developing a process to improve the mud produced after arsenic evaluation with iron. And then Maria Aurora Armienta, she says, excellent presentation and important information. Congratulations, Prosum. Maria Cecilia de Mergazo, it's also a congratulation. It's congratulating this presentation. Gopal Krishan, it's excellent presentation. Thank you, Professor Prosum. Very well presented, very informative. Regards, Junaid Ali Khattab from Pakistan.
Thank you all for.
And the last question I'm going to read is, hi, first of all, congratulations. I'm PhD student Angeles Rodriguez from Argentina. I wonder if this technology you have developed, it's the best, that's the same question as Jessica, so I'm not going to, it's about asmitas. Yeah. Prafuya Sahu, thank you so much, Professor. And now the last question, also from Cecilia. I have not seen Buenos Aires spot of arsenic concentration in the map. Well, it's an observation more than a question. Gina Torres, muchas gracias. Excellent. Thank you very much. Excellent presentation. Gopal Krishan, he has a question. In some areas of Punjab, there was no arsenic about 10 years back, but now arsenic occurrence is found in many places in Punjab. What are your views?
This is an interesting question with Gopal Krishna. Thank you for this question. But actually, my question was that, I mean, did we really look for arsenic before? So what does the historical databases say about it? So is it that suddenly arsenic has cropped up. So it's just due to the sudden influx of groundwater flow. But again, the question is, the Punjab has been an active food basket of India. So where groundwater has been exploited over a major extent over the past several years, I mean, 2, 3, 4 decades, more than that. So when we, is it 4 decades or 5 decades maybe? So has that really induced groundwater flow systems, which facilitated mobility of arsenic, this water sediment interactions that has mobilized arsenic. So maybe, and that's again linked with that you have high productive agricultural zones that you are actually pulling in the redox drivers into the aquifers. So that's a very tricky question, but we need to have a systematic investigation to unravel these developments. So what has happened actually over the past years? Now I see you, Kark. Good to see you.
I came late. I'm sorry. I had conflicts. That was one problem, and I have problems with the time differences.
Oh,
No worries, Kirk.
no problems.
No problem.
Anyway,
Okay.
sounded from what I did here, it was really good, Prosun. You've been doing some amazing work here, you and your colleagues.
Yeah.
So we have a fantastic team from Bangladesh, facilitated through Kazim Matin and Tahmidul Islam, and then Matthias from Ramzan, from Rumble, and then Sanjeev Sharma, our digital expert. And on top of that, what we are trying to do together with my new student, or rather, he's also not young anymore. He's going to graduate soon. Julian Ijumulana, he's working on geospatial technology. Understanding, you have seen the recent papers on using the special variability of groundwater contaminants and try to locate the safe water sources. And this is again, these things which has motivated the GSS session in linking advances in natural science and application of artificial intelligence and data science. So we have huge bulk of data. So can we really look back to those data and try to do some algorithms to find out what these data say before we get into new projects and new data? So we need to do a reliability check. We need to do very special checks which area, because we have several limitations of those data and how we can really make many data which are currently, for example, if they're not usable, can we really make those informations usable, because many sources are not existing anymore, and likewise, so that we have. And but the important thing is that the universities have very fraction of the data what we have at the universities, and bulk of the data lies with the national institutions and organizations. Can we really tie up with them and to unravel the things? Like we have been publishing this paper with Abhijit Mukherjee on leveraging artificial intelligence and machine learning based on the data sets which are with the governments. And for overall risk reduction, risk prediction, and risk reduction towards policy.
Okay, President, we thank you all for your great presentation. We hope to have in the future presentation again. And yes, we invite you to our next speech that's going to be on August. Best regards, and we will be sending you more information from our next webinars in the next weeks. Bye-bye.
So I'll be looking forward to the abstracts to the arsenic session in the GSA.
GSA, yeah. Yeah. Yeah, I sent an email.
Yes. Yeah. Muchas gracias.
Bye.
Bye. Thank you.
Yeah, bye-bye.
Thank you, Prosun.
Thank you very
Thank
much.
you. Muchas gracias. Para todos.
You all.
Gracias a todos. Gracias.
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 Bye bye.
Bye. Bye.
Bye.
Bye. Obrigado.
had a huge issue with my computer this morning, and I was running two computers at the same time. I had like an electric problem. And
I would like to have it.
I
Did
had
you
to
take any
switch computers.
snapshots?
Thank God it didn't stop the presentation. I was so worried.
Yes, but you managed this problem.
It's mute. Okay, I can listen now.
Yeah.
Yeah, it was so, I was so stressed because nothing was working. Tengo que parar acá. YouTube.
Oh, yeah.
Yeah. Bye.
Bye bye.
Bye.
I thank you,
Thank
Professor.
you.
Bye. Thanks.
Thank you, Prosun.